Hello everyone, welcome to the today's MIST seminar. Just a quick reminder that the seminar is recorded. Please can you, well, if you don't want to be recorded, please keep your webcam off and stay muted. And then if you've got any questions, you're welcome to put them in the chat, or at the end, you can raise your hand and unmute and you can ask questions as well. So today's seminar is going to be given by Tim Horbury. Tim is a professor of physics at the Department of Physics at Imperial College London. Tim is the principal investigator of the Solar Orbiter Magnetometer, science lead of the IMAP magnetometer, and science lead of the Heliosphere magnetometer, science team member on Fields and Sweep on Parker Solar Probe. And today, Tim is going to be talking about the IMAP mission, an overview and prospects for science and space weather. So I'll hand over to you now, Tim.
Great, thanks very much. Morning, everybody. I'm Tim Horbury from Imperial. So what I'm going to do is talk you through the IMAP mission, a bit about what it's about, what the big science questions are, the involvement that we've got in the UK. And I'm going to try and talk near the end about how people in the UK science community might get involved and why you might want to get involved as well. So, okay, a bit about IMAP. So as I say, I'll start talking about the science. The big picture science here is IMAP is about how the heliosphere, the solar system, interact with our interstellar environment. But it's also got a big aspect about particle acceleration and propagation. So I'll talk about that as well. So I'll talk about the mission itself, the spacecraft, where it's going, the instruments on it, how we're going to operate it, and data products, that kind of stuff. And then what I think is probably going to be more interesting to the UK community is about the constellation at L1. So IMAP's going to L1, and the fact that we're going to have a fleet of spacecraft at L1 working together, which is not part of the science goals of IMAP or indeed any of the other spacecraft at L1. But I think those spacecraft together will be able to do something really quite special for solar wind science, but also actually for magnetospheric science as well. So stay tuned for that. And then at the end, I'll just tell you where we're up to and where we're going. Okay, so the big picture, IMAP's about how the solar system lives in our interstellar environment. So as Douglas Adams taught us, we're in the unfashionable end of the western spiral arm of the galaxy. And the sun, as we are all taught, the sun's hot atmosphere blows out into interplanetary space to form the solar wind, traveling at several hundred kilometers a second. It passes us with a density of a few particles per cubic centimeter. And it keeps going, but at some point it can't keep going forever. And eventually it interacts with the interstellar medium. And so the schematic on the left gives you a kind of general idea about how that interaction works. So we are going around, the solar system is going around the galactic center at about 300 kilometers a second, but the interstellar medium is going around it as well. So our relative speed to the local interstellar medium is about 25 kilometers a second. So that's an important number to kind of know. The interstellar medium itself is a very rarefied medium. It's at about a few thousand Kelvin, so it's partially ionized. So there's a thermal equilibrium between neutral gas and neutral atoms and also plasma. So it's partially ionized. There's also dust and lots of other stuff floating around as well. So it's a rather complex structured medium itself. So the whole solar system is plowing through it. So what happens in practice is that the solar wind travels roughly radially away from the sun at a few hundred kilometers a second, and eventually it has to stop in some way. So it gets shocked by what we call the termination shock. So this slows the solar wind down, shocks it, compresses it, and deflects it. And the solar wind then is deflected around this boundary and then travels downwind. The incoming interstellar medium goes through some kind of compression. So 25 kilometers a second is similar to the alpha wind speed in the interstellar medium, was thought to be. But so this is probably not a shock, but probably a wave. Anyway, it gets compressed and is also deflected around it. And there's a boundary between those two, just like the magnetopause, there's a boundary which we call the heliopause, which is the boundary between the interstellar medium and the solar wind plasma that's been shocked and deflected. So it's a slightly different environment to a magnetosphere because there's a very strong plasma source at the center here, the solar wind. But the fundamental idea is kind of the same. You have a medium which is being deflected around a boundary, and there is that sharp boundary between the two, which is called the heliopause. So that's the kind of big picture. Of course, things are more complicated. So the diagram on the left gives you a little bit of the nuance here. Again, here's the heliopause. The interstellar ions are then compressed, slowed, and deflected around the boundary. The interstellar neutrals can keep going. And because there is some interaction between the two, we expect the interstellar neutrals to actually be compressed so that to be a so-called hydrogen wall actually upstream of the heliopause here. But a lot of those neutrals can get through. So helium doesn't. Hydrogen can get photoionized, and also collisionally ionized as well. And so that generates what's called pickup ions. So they are interstellar neutrals that come into the inner solar system, get ionized, and then are carried outwards with the solar wind. So they're important. We'll come back to those later on a little bit. But some of those neutrals, particularly helium, which isn't photoionized, can get into the inner solar system, and we can measure those neutral ions directly in the inner solar system, which is why we can measure the relative flow speed to the interstellar medium so accurately. Other things that are going on, of course, there's an interstellar magnetic field as well that gets compressed around this boundary as well. Galactic cosmic rays are traveling along field lines with very large gyro radii, and so the heliopause and the heliospheric magnetic field are a very strong blocker to galactic cosmic rays. So one of the things that is of interest is exactly how the solar system blocks those galactic cosmic rays, how the heliopause does so, and so on. That's an important topic. And obviously within the solar system itself, within the heliopause boundary, things are very complicated. So the termination shock is at around about 100 AU. And because it takes years for the plasma to get there, the magnetic field is very twisted up by the time it gets there. That then is deflected and carried across. And so you get a very complicated tangled magnetic field structure that gets carried down tail as well. Okay, so that's a kind of overview of what is a very complicated picture, but that's all kind of theory. Does any of this happen in reality? Well, we know these kind of things happen elsewhere in the galaxy. So this is a famous Hubble picture of a young star in the Orion Nebula that's recently been born, is plowing its way through the nebula, and you can see the power shock upstream of the star very well. But also we have direct measurements from the solar system as well. And so the two Voyager spacecraft have been traveling since the 1970s. And are taking measurements still out there in interplanetary space far beyond Pluto. And this is a plot from John Richardson's paper. So this is one of the Voyager spacecraft. So look at the distance scale here is in astronomical units. The top panel here is the radial proton speed, and then proton number density and proton temperature. And so you see a few hundred kilometers a second solar wind. It gets a bit weird out in the outer heliosphere. Here's the termination shock. You see that the wind is slowed down as we go into the heliosheath, which is the shocked solar wind plasma that's deflected. The proton number density drops off, and then you see it sort of equilibrates after a while, and that's really because the very large loading with pickup ions later on. So actually, there's a lot of pickup ion density in the solar wind by the time you get to the termination shock, which makes it a very unusual medium. So there's a slight compression, and then we go into the heliosheath. And the proton temperature, again, sort of adiabatically cools to start with, and then does not. Again, that's turbulent heating, but it's also heating from the pickup ions. But then there's obviously large heating at the shock itself. So we have really good measurements from the two Voyager spacecraft going through the heliosheath. And in fact, both of them have now gone through the heliopause, and both of them are in interstellar space. And this is an example plot of Voyager 2 going through the heliopause itself. This is just magnetic field data. Look at the scale here. This is years. Everything happens slowly. The top plot here shows the field magnitude in black and then the components. But the bottom two panels show the angles of the magnetic field, and actually it's probably a more useful way to look at it. You can see inside the heliopause, the magnetic field is quite messy and complicated, because remember, this is all shocked solar wind plasma, essentially. You can see there's still the remnants of the sector structure in here as well. And then we go through the heliopause boundary into the interstellar medium. So this is the compressed and deflected interstellar medium. But you see here, things are much more smooth. The scales are much larger. And so it's a really sort of steady, smooth medium, which is no great surprise, I think. And on the right-hand side, this is just a zoom up of that transition. Again, field magnitude. There's a kind of transition region here, there's so-called magnetic barrier, until we go through the heliopause proper. There are the angles. And at the bottom here, this is fluxes of very high energy galactic cosmic rays. And you can see here just how effective the heliopause is as a barrier to those particles. So you see the strong gradient across here as well. Okay, so that's great. But there are two Voyager spacecraft. They're quite old. Their instrumentation isn't optimized for it. We really want to have a look at a global picture of what's happening at the interaction. We can do that using energetic neutral atoms. So this is a single solar wind proton traveling away from the sun, ending up in the heliosheath. And as those particles travel outwards, they start encountering interstellar neutrals or neutral particles, but any sort, generally interstellar neutrals. That's these little blue things with little red electrons around them. I hope you can see the movie. We can do a charge exchange. And at that point, the solar wind proton becomes a neutral and just travels in a straight line in any given direction. And one of the directions it could travel is back towards the inner solar system to land in the detector of a spacecraft close to the Earth. It's unlikely, there aren't many of them, but it does happen. And we have instruments that do exactly that. And there's a spacecraft that does exactly that, and that's called IBEX. So IBEX, there's a little kind of sketch here on the right. It's a little baby spacecraft. It's I've never seen it, but apparently you can hold it in your arms. It's so small. So it was launched in 2008. And it's a low-budget spacecraft as well, so a total budget about $100 million. And it was dedicated to doing what we call energetic neutral atom imaging of the heliosheath and the interaction between the solar wind and interstellar space. So energetic neutral atoms are basically neutrals traveling at high speed. So the solar wind ions that are going out are doing a few hundred kilometers a second. So when they charge exchange and become neutrals, we expect those atoms to also be doing a few hundred kilometers a second. And to give you an idea, a proton at a few hundred kilometers a second has got an energy of about 1 keV. So we're looking for things of the order of keV or so. So basically what happens is you have that charge exchange. Some of the atoms go in whatever direction the ion was traveling at that moment in time, gyrating around the field or whatever. But some of those can be traveling back towards the inner solar system. And they essentially fly on ballistic trajectories back to the spacecraft. And so when we look outwards, we look in a particular direction and we see ENAs coming back. Then they are basically the flux of those coming back at a given energy is basically the line integral of the charge exchange rate that is happening along that line. So we're basically looking through the heliosheath and that interaction and seeing the ENAs that come back. So these are very difficult measurements to make. They're very subtle, but they provide information in a global sense that is otherwise not available. So say IBEX launched in 2008. And it made some really interesting measurements. And in particular, it made a totally unexpected discovery, which is still to a large extent enigmatic. And that's something called the IBEX ribbon. So on the left-hand side, you can see an all-sky map of ENA data. So this is the ENA flux measured by IBEX High, one of the instruments. So again, this is about a keV, so a few hundred kilometers a second protons, essentially. And so this is a map looking across the whole sky of the fluxes. So from and you look at the counts here; these are very, very low counts, and this is a complex differential flux measurement. But whatever, these are very, very low fluxes. We're used to things like solar wind measurements where we measure fluxes across different look directions and bins, and we talk about VDF, this kind of thing. These measurements are not made that way. They count individual atoms that arrive into the detector. So these maps are built up over about 6 months. So it takes a very, very long time to get usable fluxes. I'll come back to that later on. Okay, so in this map, the nose, so that's the direction that we're traveling through the interstellar medium, is marked there as the dot, and the locations of Voyager 1 and Voyager 2 as they're traveling outwards through the heliosheath are marked as well. And what's most striking here is this feature here, which is nearly a great circle. It's actually not quite a great circle. And that's been called the IBEX ribbon. Totally unexpected, not predicted by anybody before IBEX launch. So obviously this was a big thing at the time. It got a couple of signs and so on. And since then, people have been trying to understand why this is there and what is actually happening, why it's the way that it is. You can see the sort of working theory here, which is related to the interstellar magnetic field. And that the interstellar magnetic field is essentially draped around the, this is supposed to be a schematic of the entire heliosphere, the heliopause, as we're traveling through the interstellar medium. And the idea is that the ribbon basically delineates the line where that draped magnetic field is exactly perpendicular to the boundary for reasons that, well, perpendicular to the line to the Earth, essentially, which we'll come back to. So yeah, when it was the ribbon was discovered, there were lots of theories, and since then there have been lots of theories about why. I'm not going to go into this in any great detail, and to be honest, I'm not an expert in it. The ENA community is a small one, so most people have not worked on ENAs. I certainly haven't. There may be 1 or 2 people on this call who have, but I suspect on average, if you're listening to this, you haven't worked on ENAs. but there's a lot of information in them. They're very, very rich, and there's the community that works on it actually has been doing an awful lot over the last few years to try and understand this kind of these data and what they mean. So the working theory for the ribbon, or the most likely one, perhaps the most widely accepted one, is that these are essentially a secondary ENA, so a double charge exchange that has occurred, and essentially these are pickup ions that travel outwards. They then get neutralized and become atoms in the heliosheath. And at these points where the magnetic field is draped, they can essentially sit, if they're at high pitch angles, they can essentially sit and stagnate. They can sit and essentially hover in space for a long time, potentially years, and eventually do another charge exchange with the solar wind ion and then come back towards the solar system. So that's the kind of working theory. There are lots of challenges to get the kind of fluxes that are measured, but that's the kind of best bet at the moment. Okay, so as I say, the ENAs give us a global measurement. The Voyager spacecraft gives us a local measurement. And so the challenge is to try and link these two things together. And one of the real challenges with IBEX, although the data is really interesting, it's really low resolution, both temporally and in terms of angular resolution as well. For example, there are hints of things like striations in the ribbon, but nobody really knows whether that's true or not. It's really difficult with the data to find out. And the diagram on the right just gives you an example of where modeling suggests that the fluxes of ENAs from the ribbon come from as a function of energy. It's slightly different because of the way the field is draped. And you can see the Voyager spacecraft are slightly irritatingly not actually running along the ribbon, but nearby. So a lot of modeling, a lot of this is based on modeling as well. But really, to make progress, you really want to make better measurements. And that's kind of what IMAP's about. A great advantage of IBEX running for a long time is you can actually see how the ENA flux varies over time over the solar cycle. So this is at slightly higher energies. This is 4 kV. At these higher energies, you don't really see the ribbon as much. You can a little bit, but you can see here the flux has really changed dramatically over the solar cycle. So these are individual yearly maps, and you see the fluxes really go down, and then they start ramping back up again. And you can even see things like as we ramp up. So basically, this is because the propagated solar wind dynamic pressure increases out into the heliosheath, and so you get a higher density of particles there, which can then do the charge exchange and come back. So the flux has really dramatically changed, but you can see it's actually asymmetric as well. So you don't necessarily. So here, for example, the southern hemisphere brightened before the northern hemisphere, and that's thought to be related to latitudinal variations in the solar wind ground pressure, even that you can measure at 1 AU, for example. So there's lots of really interesting stuff here. But as I say, these maps are great, but they're very limited in what we can do with them. And so to make progress in this field, which is, I think, a really interesting one, a very enigmatic one, one needs better data. And that's one of the key arguments for IMAP. The other aspect of IMAP science is to do with particle acceleration. So IMAP, as we've talked about, we have these ENAs, and they come from ions, and in particular, pickup ions that generate some of these things. And so we really want to understand the life of pickup ions and other energetic ions. So IMAP has a science target as well, particularly on superthermal particles. So not so much on very high energy particles, but IMAP is interested in the acceleration of particles at shocks and their propagation, and superthermals in general, including pickup ions. So it's interested in composition of superthermals in the solar wind. And so it has a payload, as well as looking at these ENAs, it has a payload to look at things locally at the spacecraft, solar wind, magnetic field, and superthermal ions in particular. So the plot on the right-hand side shows, this is basically a plot of the particle fluxes as a function of energy here. So this goes from 1 kV, so this peak here is the solar wind, and then you get sort of pickup ions, the superthermal, these are the kappa tails, and then up to very higher energies, and then ultimately galactic cosmic rays. And if you look at the middle panel, this shows the energy range for the various instruments that are measuring. So first of all, IMAP low and high and ultra are ENA instruments. But if you look at the solar wind one, so SWAPI is the bulk solar wind instrument, which of course measures the bulk solar wind beam. CODIS, which is the superthermal instrument. So that's an instrument that measures superthermal particles, pickups, shock accelerated particles. And that instrument does composition. So importantly, we will be looking at different ion species and how they're accelerated at interplanetary shocks, for example. CODIS home, CODIS high, and then we also have HIT, which looks at higher energy particles and off into not quite an MeV, but certainly tens of hundreds of kV. Okay, so that's quite a broad range of energy resolution as well. And I should say as well, I'll come back to this later on, because IMAP is measuring in situ data and it's doing it at L1, it also has on it something called iAlert, which is a real-time space weather beacon data as well. So I'll come back to that later on. Okay, so let's talk a bit about IMAP, the spacecraft. So here's IMAP. So this is an image of it on the right, taken a few weeks ago. The mission PI is Dave McComas, who's now at Princeton. And this is a NASA mission, so it's the 5th in the Solar Terrestrial Probe line. STP has in it things like MMS, Stereo, the American contribution to Hanoda, things like that. It's of order, I mean, on the way towards $750 million with the launch as well, that kind of order. So not a huge class mission, but it's not a tiny one either. Designed and built at APL in Maryland, so some of us have got quite used to going to APL now. It's a sun-pointing spinner, so it spins at 15 seconds. It's got a 3-meter deployable boom for the magnetometer. There are 10 instruments on board. I'll show you those in a minute. 2 of them come from outside the US. So one of those is the magnetometer from Imperial College, and the other is an ultraviolet instrument called GLOWS, which comes from Poland. So we're launching on a SpaceX Falcon 9, and spacecraft don't often go to L1, so it's carrying some other spacecraft with it. One of them is SWIFO L1, so that's a NOAA mission, which is also a space weather mission, so it'll carry a coronagraph as well as in situ measurements, and Carruthers is a NASA mission to look at the geocorona. And then we'll inject into the L1 halo orbit. And I think just as an aside, I would say anyone who's worked on a mission knows, missions are spacecraft and instruments, but they're also people, and the IMAP team is enormous. This photo is just a snapshot of some of them have happened to be in one place at the same time, but it's an enormous team of people that get these things done. Okay, so here's the science payload. So we have 3 ENA instruments at different energies. So IMAP low, it's on what's called a pivot platform. It rotates around to look at fluxes from different directions. And then IMAP high and ultra, so this is gradually going up in energy. There are 2 of each of these 2 detectors. So there's 5 ENA detectors in total on the spacecraft. Obviously, the magnetometer, the best instrument. There's a solar wind electron instrument. SWAPI is the ion instrument. It doesn't produce full 3D VDF. SWAPI is actually a copy or an evolution of the instrument that flies on New Horizons, so you don't get a full VDF from it, but we'll get solar wind data. And then CODIS is this instrument that does superthermal, so I think that will be a really interesting instrument for the in situ science. That's kind of where the new in situ science is coming, I think, and then HIT for these higher energies. And then we have a big dust detector to look at interstellar dust, and then GLOWS for the UV. So, okay, so how does IMAP make ENA maps? Well, so this is, for example, one of the instruments, 2 sensors. The spacecraft rotates as it goes around the sun, and then we have these look directions. And so as it looks, it counts. And as we go around the sun as well, we gradually build up this map. So it takes IMAP, IBEX about a year to make a map, sometimes 6 months if you're pushing it. So IMAP will make those maps much more quickly. The detectors are much larger, so we get much better fluxes and we get much better angular resolution as well. So we should be making far, far better maps than IBEX straight away out of the bat. So this will happen very quickly and we'll get really new data very rapidly. So 10 instruments, it's a really busy spacecraft. So this, what they call the disco ball animation, just kind of shows you all those different detectors on the spacecraft. The spacecraft is kind of like a Trivial Pursuit wedges of cheese. It's actually built in this honeycomb structure with a set of angular bays, and each bay has multiple instruments in it. And so they all have to have look directions which are designed so that they don't interfere with each other and whatever else. So it's all rather complicated. That's the high energy telescope. And so gradually, so this is CODIS, so that's the high energy part of CODIS, and then you'll see the lower energy part of CODIS. So again, that's the one that's going to be looking at the superthermals, which I think will be very interesting. And then you can see the solar rays on the top. So the sun is straight up in this view, and as I say, it spins every 15 seconds. And as you'll see as well, the magnetometer boom as we rotate around. So the 2 Imperial College sensors are at the end of that boom. So they're installed on, and we've been doing some, we've done some what they call pop and catch release tests on the boom, and all of that is working very well. So that's the full disco ball. So you see it's a really busy spacecraft. There's a lot going on. Okay, if you're interested in what IMAP is up to, you can actually follow along. There's a live feed from the clean room, and actually later on today, they should be integrating the final instrument CODIS. So have a look later on today. If you search for IMAP Princeton on YouTube, you'll find it. This was a screenshot from just before, whatever, 40 minutes ago or something. And so they hadn't started working yet this morning, but they were only just getting up. Okay, so I want to talk a little bit about the IMAP magnetometer, just because I'm biased. So we're providing the magnetometer for IMAP. We were approached by the project quite late on. It had already, the mission had been selected, but the original magnetometer provider couldn't come through, so we were asked to provide one. So, so this has all happened in rather a hurry for us, but we are responsible for all of the IMAP magnetometer design, build, operation, and we'll be doing the in-flight calibration at Imperial College as well. It's a digital fluxgate design, so it's got a lot of heritage from Solar Orbiter. There are some slight modifications. We had to change the data interface to UART, and we've taken some aspects of the juice magnetometer power supply. We don't need sensor heaters because we don't get cold, that kind of thing. One thing we have done is we've implemented data compression, so that gives us roughly a factor of 2 increase in data compared to the original baseline. I'll talk about that a little bit later on. And for Solar Orbiter fans, we've just rebooted last week the Solar Orbiter magnetometer into a new version of flight software, which implements the same compression algorithm. It's working well in flight. It's been working well over the weekend. So that is significantly increasing our Solar Orbiter data return as well. Okay, so as I said, we've got 2 sensors. They're on a single boom, single hinge boom. The flight model is fully functional. We delivered it in March of this year. It was being installed on the spacecraft. It's been on the spacecraft for a long time. It's been operating. It actually operated yesterday afternoon during a test, for example. It's working really well, so we're very happy with it. And the final version of the flight software is at 1, so we are done. We're funded by the UK Space Agency, and if you've never built a flight instrument, this won't mean anything to you, but if you have, it will. We went from first funding to flight model qualified and integrated onto the spacecraft in less than 3 years, through actually partly a pandemic as well. So this is a testament to the quality of the engineering team here at Imperial. They did an amazing job. Okay, here's just some pictures just to show you we did actually do some work. So we go through environmental test with the flight model. So this is vibration test, thermal vacuum test. This is calibrating the instrument in Germany, electromagnetic compatibility testing. Then the sensors were installed on the boom, and then finally the boom was installed on the spacecraft. So you can see the boom here between the solar array. The magnetometer itself is great, as you would expect. So this is just some data in a shielded can at Imperial, just to show you the stability and the noise level of the instrument. And this is a power spectrum. Again, if you're not an aficionado of magnetic field data, you don't need to worry about this, but this is very good quality and very good quality data. So we're very happy with that. And if you ever wonder how hard the engineering teams work on these instruments, you just have to look at the timestamp on that data. Okay, so in terms of the data that the magnetometer will produce, MAG will be on continuously. We're going to be on from launch plus 3 days. We'll be on throughout commissioning as the spacecraft moves towards L1. And actually that by itself, I think, will be interesting data. So we will be obviously traveling essentially upstream of the Earth at a progressively increasing distance, and we'll get magnetic field data all the way through that. So I think that comparing to an Earth baseline will be very interesting as well. So if anyone's interested in that in terms of even things like space weather and whatever, then do let me know, because that will happen very quickly after launch. Okay, in terms of data modes, things are very straightforward. IMAP's philosophy is to really minimize operations, keep everything as simple as you can. So we've got what we call the normal mode, which is 2 vectors a second from both sensors, and that will be on essentially all the time. And then we have a burst mode. So when we came onto the project, we inherited a burst mode of 15 minutes a day, which I don't think is adequate. We've been working really hard with compression, but also trying to make things as efficient as possible. And we've managed to work that up within our telemetry budget to about 8 hours a day, which is rather more reasonable. We really want to be in burst mode in an ideal world when we go through a shock, because 2 vectors a second isn't really good enough to resolve any details in the shock. So we really need higher resolution. I said we also have space weather beacon data called iAlert, and that will produce 1 magnetic field vector every 4 seconds. And that will be telemetered in real-time beacon, just like DSCOVR and ACE and so on do now. The space weather data go public in real time. I mean, that'll be less than 5 minutes after receipt of the spacecraft. All the science data go public 3 months after receipt on the ground, so it'll all happen very, very quickly. We have internal data products within the project, which will happen essentially immediately. The science data is getting processed at LASP in Colorado. And the way the systems are working is that the data actually gets processed there, and the preliminary data products are generated immediately without any input from the instrument team. So everything happens very, very quickly. And obviously, internally in the science team, we have access to the data pre-release. So if people are interested in getting involved, please let me know. Okay, so the magnetometer science, I'm not going to go into this in any great detail. Obviously, magnetic field instruments are the most important instruments, and they are important for almost everything we do in plasma physics, so I won't belabor the point. But the kind of targets that we're interested in are magnetic field structure and the way particles propagate through them, wave-particle interactions, shocks in particular for acceleration, and then general turbulence and solar wind structure. And just to give you an idea, this is a solar orbiter magnetometer measurement of a shock transition. So this is the kind of data we get routinely from orbiter, and we expect to see the same kind of thing where we can resolve the upstream wave structure really well. And one of the IMAP targets is really understanding those wave-particle interactions. So we're looking forward to all of that. But there's something else, and this is, I think, where the UK community is probably going to be most interested, because we're going to have a fleet at L1. So IMAP is launching, it's taking with it SWIFO, which also measures things in situ at L1. So at that point, when those two spacecraft arrive, there will be 6 spacecraft taking in situ. By in situ measurements, I mean plasma and magnetic field. 6 of them at L1 for the very first time, and this is a big change. So historically, there have been 3, which is WIND, ACE, and DSCOVR over the last few years. Aditya-L1 launched last year and has magnetic field and plasma data as well, and seems to be working really well. And then IMAP and SWIFO will join them. 6 spacecraft at the same time taking measurements in the L1 halo. And this is really important, and it lets us do things we couldn't possibly do before. Obviously, in the UK, we're very experienced in multi-spacecraft constellation data, like cluster, and some people work on NMS and whatever else. 4 is good, 6 is even better, and 6 gives you 15 simultaneous baseline measurements. So that, for example, in understanding the 3-dimensional structure of the plasma, this is extraordinary. We've never had anything like it anywhere else, so that would be extremely valuable. And it lets us do a whole set of things we just haven't been able to do before. And for those of us who aren't really familiar with L1 and the kind of scales that we're talking about here, this plot at the bottom right has, it's got the plots of ACE, WIND, and DSCOVR nominal orbits. WIND is rather larger than the others, and you can see that from this table as well. But it's also got plotted on here the black circle, and the black circle is essentially the cross-section of the magnetopause. It's not at the center on this plot because of solar wind aberration, because we're going sideways at 30 kilometers a second. So that introduces a non-trivial aberration angle you need to be aware of. So if you're interested in magnetospheric physics, then we normally use some kind of upstream L1 monitors to try and work out what's going on one of those spacecraft at any given time. But you can see from these orbits that different spacecraft are better lined up with the magnetosphere at different times. But also, when you have multiple spacecraft, you can actually start looking at the 3-dimensional structure of the solar wind. And I think this is one thing that we really will be able to move on from what we've been doing up to now, which is this idea about, I measure something at L1 and I assume there's just a radial phase front and this stuff just streams across the magnetosphere. It just isn't true. The solar wind is really structured on these scales. So the L1 halo orbit is of the order 100 RE. 100 RE is roughly the correlation scale of the solar wind. So things vary on that scale. So I think with multiple spacecraft for the first time, we'll be able to really look at how the structure of solar wind arrives at the magnetosphere. I think this is going to be a real step change in understanding space weather driving. Okay, so what are the kind of science targets that we can achieve then with this constellation? Well, as I said, we can look at the solar wind plasma at the correlation scale, which we've never been able to do before. This plot here shows you essentially the autocorrelation in the solar wind. And if you look at the kind of scales we're looking at here, the things that we look at with MMS and cluster are really at very low separation scales compared to the correlation scale. It really tips over here, and this is roughly the scale of the L1 halo orbit. So we will be able to measure this large scale. So this is what you might call mesoscale structure. So this is the transition from structure to turbulence, which we've never been able to look at in 3D before. So we can look at how the structure is decaying into turbulence and how that works, how the turbulence is driven essentially. For example, we could look at a switchback in 3D. Switchbacks go past L1. Nobody knows what switchbacks look like in 3D, so we could look at things like that, for example. And as I say, how turbulence is interacting with what's called the outer scale of the fluctuations. In terms of shocks, by having multiple measurements of the same interplanetary shock going past, we can look at how the shock responds to varying upstream conditions and things like rippling and reformation, foreshock variability. So this is a nice paper by Domenico Trotta from last year, where he used WIND, DSCOVR, and ACE data at L1 to see how the foreshock varies on really quite small scales, and you can see shocklets here. and then propagating that towards the Earth as well. But again, with more spacecraft, we can do a lot more of that. Energetic particles, how the energetic particle fluxes vary by how the shock properties vary for the same shock, for example. And as I say, we can look at the structures of solar wind. And I think this is going to be really important for understanding magnetospheric variability. I think in terms of magnetospheric physics, we're really moving beyond this single idea of a global driver. And things like SMILE are part of this kind of idea as well. So I think that would be really important. We can do multi-spacecraft Grad-Shravanov reconstructions to try and look at the full 3D volume, for example, as it arrives at here. And this is important for real-time space weather as well. So multiple spacecraft of that set, at least 4 of them, will have real-time beacon data. So at the moment, nobody really combines the data from multiple spacecraft in real time to be able to make better forecasts. So how can we use multi-spacecraft real-time data to improve our forecasting from L1? We've been looking at stuff at Imperial College. I've been running some projects and things on it. So we've developed some methods, and there's a diagram here from Ben Boyd's project, and then more recently from Ned and Logan's project, where you can see by combining data just from DSCOVR and wind, that's the multi-one, you can see we basically get, this is the agreement between our predictions of the SIMH, geomagnetic index, the 1-minute SIMH index, compared to predictions, compared to the real data, statistically, on the basis of either using single spacecraft or multi-spacecraft. And you can see multi-spacecraft does significantly better than any of the others. So there are ways of combining data to make better products in real time. And I think that's something we really should be thinking about. And so if anyone here is interested in space weather stuff, then please talk to me. And we have a real opportunity here to do something significantly better than what we've done before, something really new. We need to think about that before we launch. So I would encourage you to please think about that and get in touch. Okay, so where are we now? Well, as I said, the IMAP spacecraft is nearly complete. And in fact, the 10th instrument should go on today, if everything goes to plan. And then after that, we kick into gear and we go into environmental testing. So next week, it's going to head off to do shock testing at Goddard. It's then going to come back for vibration in January. It's then going to head to Marshall Space Flight Center, where it's going to do the very long thermal vacuum testing. It takes more than a month. And then it'll go straight from there to the Cape. So it should arrive at the Cape something like May next year. And then it will launch on a Falcon 9 not earlier than July next year. The precise launch date isn't fixed yet. So for those of you that haven't fallen asleep during this talk, you will notice that the picture on the right is not of a Falcon 9 rocket. In fact, that's a Saturn V, and that is Apollo 11. Apollo 11 launched from Launch Complex 39A, and I am childishly delighted to have discovered a week or two ago that the launch site for IMAP has actually changed. The pad has changed. They also launched from pad 40. So they've changed to pad 39A. So although this isn't a picture of IMAP launching, this is a picture of the exact spot on the Earth from where IMAP will launch. And it's one of the coolest, most significant locations on the planet, I think. And I am so pleased that we're launching, just from a personal capacity. Okay, so we launch. I say boom deploy, and mag will go on at launch plus 3 days. So everything's going to happen very fast. So it's all going to be a fanatic at that point. Frenetic. And then we have about a 3-month cruise to L1, where we will do commissioning as we go. And then we will go straight into science operations as we go into the L1 orbit insertion just over 3 months after launch. And then 3 months after that, the science products start being released. So everything will happen very quickly through the second half of next year. IMAP has a 2-year nominal mission lifetime, but obviously, assuming everything goes to plan, then it should have consumables for considerably more than that. Okay, so then to summarize, IMAP is a mission to understand how the solar system interacts with the local interstellar medium. And it does that through energetic neutral atom imaging of the interaction between the heliosheath and the interstellar medium. But it's also got a significant science interest in energetic particle acceleration and propagation, and obviously the magnetometer will contribute significantly to that. But also, as I've argued, it will be part of a fleet at L1, and I think there is enormous science value in combining data from those multiple spacecraft at L1. That's difficult for various reasons, practical reasons, in terms of like common coordinate systems and data formats, getting trajectory data in the same format and so on. There are some political challenges there as well, because this is a multi-agency problem. There are NASA spacecraft in that mix. There are NOAA spacecraft in that mix. And of course, there's an Indian spacecraft in that mix as well. So we have already begun discussions between those different projects. I'm part of those discussions between the instrument teams to try and make sure that we can end up with science products that are useful for everyone in an easy to use way. I personally think that we would benefit from a Python package, which would let you bring together these different data sets, convert them into the same coordinate system, get the trajectory data coordinated and that kind of thing. If there's anyone out there who's interested in contributing to something like that, again, let me know, because I think that's something that that would have enormous value for the community. Again, real-time solar wind data is going to be important, so please do, if you're interested in it from a space weather forecasting point of view, please do get in touch as well. We're launching in the second half of next year. Maybe that doesn't feel very long, and it feels like a long time to you. It doesn't to me. We're getting really close now, and the data will all happen very quickly. It's not like some interplanetary mission where we have years of cruise. We're just going to hit the ground running. So if you want to get involved in this and want to make a contribution, and you think that IMAP data will be useful to you, then please do get in touch. Okay, that's it. Go IMAP. Thanks very much.